Well, hello again. Welcome back to Engineering 201 Electrical Fundamentals, and we're coming back to a new subject, but a subject that's going to require us to use a lot of our old skills in terms of node analysis and circuit simplification and so forth. That new subject is operational amplifiers. Oftentimes just op amps for short, and the reason for this is important. Let's say that we have a laboratory experiment and we're gathering some data, and the results come back like this, a very small anemic signal. So maybe this is over time, and this is some output. Maybe we'd have some a voltage output that, and we have a hard time reading that, recording that, or doing anything to that. So what we would like to do is run that signal through an amplifier and essentially then increase that signal. Okay. So we want to amplify that signal. Now, unfortunately, if you have noise in this signal, you'll amplify that too, and we'll talk later next term and source third term about how we could use filters to try and filter that out and things like that. But anytime that we have a small signal and we'd like to increase that signal, or maybe even do some things like arithmetic, multiplying by 2, or doing integration or differentiation, something like that, we can use an operational amplifier to do that. And really with operational amplifier, we can build a very specific analog computer. You might say, well, why would you want to do that? Well, for a small and specific task, an analog computer can be very efficient and also very fast, a lot faster than a digital computer. So let's wade into this. The symbol that we're going to be using for this looks like this. This is the operational amplifier. Looks like that. And there is a positive input and negative input. This is the inverting input and the non-inverting. And this is the inverting. So these would be the inputs, and then we have, of course, the output. And you'd have to power this thing. If you have ever thought about maybe a stereo amplifier or something like that, you have the input from the tuner or the whatever is getting the signal, and you have the output to the speakers, but you also have to plug this thing into the wall. It has to have some input power. So usually we'll say that this is VCC minus and VCC plus. Those are our powers. What this looks like on the inside is one way to model this. We could talk about this as being the V plus and V minus. And if I were to put this into a circuit model like we might recognize, everything's going to be referenced off of a ground like this. And this would then be our V plus, and this would be our V minus. So from up there to there is V minus, and then up there is our V plus. And we're hoping that this input resistor, Ri, we'd like this to be as close to possible to infinity. We would like it to be very large. And then this is what this is going to be doing, is this is going to be controlling a voltage-controlled voltage source. Like this. We'll have an output resistor, and then this is going to be V out, if you will, which would be across there. This R out, our output resistor, we would like it to be as close to possible as 0. We couldn't have it at 0, but we'd like to get it very, very small. So here, what's controlling this is some gain A times the difference between V plus and V minus. So I'm then subtracting. That's V plus minus a V minus. So the gain here, the internal gain, Not to be careful when I talk about gain, because the entire circuit will have a gain, but if I talk about the internal gain here, we would like that internal gain to be very large. We'd like it to be infinity. Obviously, we probably can't get that, so at least 10 to the 4, at least 10,000 minimum. Okay, so this is what is essentially going on inside of that thing, and I'll show you in a moment. It gets even more complicated than that. Well, how do we use this thing? This is going to be a chip package. When we get down into lab, we'll have a chip that looks like this, and it has 4 legs on each side. I didn't do very well spreading those out. So we have pin number 1, 2, 3, 4, and then 5, 6, 7, 8. And you know where 1 is because of this notch. The notch is always there. Sometimes there's a little depressed circle right there, like that. And that, incidentally, in chip numbering is always the same. If they have more pins, the numbers will count larger down here, and you always start back up. But the inverting input is always in pin number 2. So this is inverting. And here is your non-inverting. So that's your inputs. Then 4 is minus VCC, and 8 is no connection. This is your plus VCC right there. Well, minus VCC and plus VCC. 6 is your output, and 8 and 5 aren't necessarily connected. So you've got your inputs at 2 and 3, and your output at 6. What this looks like in real life then is right here. You can kind of see it. This is actually the chip. Doesn't look like it shows up very well on the video. But that's the actual chip, so most of you have young eyes, so you'll be okay in lab. If you don't, bring your glasses, because they're a little hard to see. This I've measured off an inch here. We're going to be using the 741 chips from the 741 family, and I'll get some information for you on that in a moment. But that's what the chip actually looks like. That's what we're going to use to give you some idea of size. There's the typical Sharpie with it, and there's an inch. So, and you definitely want to have this. You may want to print that page out, bring it to lab, so that you have that pin diagram. I'll put this enlarged one into the PDFs also. Well, what can we do with that thing? How do we analyze it and deal with it? Let's talk about that. So, if I maybe go back to the circuit that we developed here, I'll maybe quickly reproduce that so we can talk about that in a little different context. And all of these voltages are with respect to this ground state down here. Okay, and this is V out or V naught. Okay, so if we look at this, I can say that V out, the voltage across here, V out, is equal to A times, because we're hoping that this resistor is very, very small, right? Hoping that's about 0. So if it's small enough, we can say that the output voltage there is simply equal to A times V plus minus V minus, right? Okay, so the difference between those two voltages. And this is, sometimes they refer to this A as the open loop voltage gain. But we said it was our internal gain. You could have those are both common designations for that. We know that this V out has to be between our plus and minus VCC. So minus VCC and plus VCC. For instance, if we go back to this figure on page 1, this is what we're powering. This one here and that one there. That's how we're powering this thing. And we wouldn't expect to get more signal, more voltage out of it than we were putting in terms of when we power it. We're going to increase the input signal, but we can't increase it beyond the power that we're putting into it, or the magnitude of the voltage that we're putting into it. So VCC is usually somewhere less than or equal to 20 volts. We're actually going to use 15 volts in lab, and that's probably more common. Okay, and we said that A was somewhere we would like it to be as large as possible, but it's got to be larger than or equal to about 10,000. So if we throw these two quantities up into here, recognizing that V out is limited by plus and minus VCC, that's limited by plus and minus 20 then, and A is 10,000, we get what? V plus minus V minus has got to be less than, what, about 20 divided by 10 to the 4, that 10,000, which gives us about 2 millivolts. Is that right? I'm going to take my V out that's limited to about 20, divide by that A, I get about 2 millivolts for that. So what I'm going to say here is my conclusion here. Therefore, V plus is equal to V minus. They don't differ by very much. Okay, and we're going to call these our linear operation. And the reason for that, I'll come back and talk about that, but let me try and justify that. If I look at a graph here of V out versus V plus minus V minus. Okay. I'm going to get something like this. It's going to have this region here, this linear region, and then it's going to turn and go like this, and that's going to happen at VCC over A, and it's going to do the same thing over here at minus VCC over A. And this is going to happen here at whatever our VCC is. Positive VCC, here minus VCC. Positive 15, minus 15, positive 20, minus 15, whatever that is. And this region here we're going to call positive saturation. And here we're going to call this negative saturation. Okay, and the region here, that's linear. Okay, so for linear operation, when we're in this region right here, for linear operation, I know that V plus is equal to V minus. Okay, and that V plus is equal to V minus. And sometimes they'll label this as V2 over here, and this as maybe V1, and we'll say then that V1 is equal to V2. That is, the voltage of the inputs on our operational amplifier is equal to each other. That is, or back over here, the voltage across here or the voltage across there, since they're equal to each other, the voltage difference should be 0. Okay, so that's going to be important. That's going to be important. And for our purpose in here, again, the electricals are going to go a lot further along and talk about what happens when you get into saturation. We're going to concentrate strictly in the linear region. So we're always going to use linear operation. That's going to make our life a lot easier. The last thing to mention here is nature tends not to like these nice corners like this. This looks good on the graph, but when we go into lab, one of the things you're going to do is you're going to build a saturation curve, and you'll probably find that your saturation curve has a little bit of roll-off like that, which is actually fine. Well, let's come back and look at this diagram here a little more. And we said that we had this scenario here about, we had this resistor, and we had that V positive, or sometimes we'll call this V2, and we had V negative, sometimes we'll call that V1. Anyway, we said that V negative was equal to V positive, or V1 was equal to V2, or the gist of that is that that's 0 volts across there. Okay? And we hoped that this input resistance, remember we were talking about this input resistance, we hoped that this was equal to about infinity, that it was very large. So with virtually no voltage difference across here and a very large resistor here, Ri is large, okay, we'd like it to go to infinity. What can I say about the current here? If I talk about the current I positive, or the current here, for that matter, I negative, what can we say it is? We can conclude then, for linear operation, that the voltages at these 2 points are not only equal to each other, but the current, that is I plus, the current into the positive terminal, or I negative, the current into the negative terminal, is equal to 0. So the voltage here and here has to be equal to each other. Isn't that what we said? Yes. There's no requirement that it be 0. It has to be equal to each other. Sometimes it's 0, sometimes it's 10 or 15 or whatever, but it has to be equal to each other. And then the other big help is in linear operation that the input currents are equal to 0. They're not only equal to each other, they are equal to 0. Well, that's a lot of new symbols and sometimes fast talking. Let's put this into an example. So, probably just start a clean sheet. We might, again, just wrap up. All we're going to do is linear operation. So for linear operation, we can say that V plus is equal to V minus is equal to, I'm not real sure, sometimes it's 0, sometimes it's not, but I do know that they're equal to each other. And I can say that I plus is equal to I minus, and I know that's equal to 0. So that's what I get when I've got linear operation, and all we're going to do is linear operation. The electricals will go on next year and talk about a lot more, but we're going to concentrate on linear operation. So with that at hand, let's move forward and try a couple examples. And I think you'll see that, again, probably the most difficult part of this is the circuit analysis, and not necessarily the assumptions and whatnot. So let's say that I have a circuit that looks like this. Say that I have 1 volt here, and I've got a input resistor. Okay, so I'm going to say that this is 25 k ohms. I'm going to say that this is 100 k ohms. I'm going to talk about this as 0.1. I'm going to talk about this as 0.2. Okay, and what we'd like to do is we'd like to, given this, we'd like to find V naught. Okay, we're going to assume linear operation. We'd like to find V naught. Well, the way you do these, and these problems can get almost boring, is because we always use Kirchhoff's law at this node up here. Okay, so if I talk about a current here, let's say I say this is I1, And maybe I won't use I1. Maybe I'll use, that would be a good one, IS. I don't want to confuse with my I pluses and my I minuses. So a lot of times we call this the source resistor, okay, R sub S. And this that goes from the input side back over here, this is very common to have this resistor here, and a lot of times we call that the feedback resistor. Anytime we have something going from the output back to the input, sometimes we talk about the feedback. So let me talk about this current here then, IF for feedback. I think I'm going to need a better pen for this. What about these currents here? I would have this current here. I could say that that is I minus, and I've got this current here that I could say is what? I plus, right? So if I do Kirchhoff's current law at 1, Kirchhoff's current law at 1, what do I get? Well, I get that IS is coming in, the source. IF is coming in, and what's leaving? So what's going in is equal to what's leaving, I minus. That's I prime, not I minus. Let's get I minus. There we go, I minus. So with that, if I assume linear operation, what can I say about I minus? I minus has to be equal to 0. So that's 0. That's good. So now let me talk about IS, and this is where you need a good command of node analysis, because you almost always do this with node analysis. So if I come in here, I've got the current going to the right, so I need to find the voltage potential going that way, don't I? So I could say this IS is really equal to getting from 1 back down to this ground state, so that'd be minus V1, right? Because isn't this voltage up to there? That would be V1. The voltage up to there, that would be V2. Talking about the voltage from here up to 2, or the voltage from there up to 1, V1, and V2. So IS would be equal to minus V1 plus 1, and then I just divide by 25K, right? And then to this I'll add IF. Well, IF is going to the left, so I need to find this potential like that, don't I? So how do I get from here over to there? Well, again, minus V1. That gets me down to here, and now plus V0, our output. So I go from there to there, minus V1, and then up to there, which is V0. And I'm going to divide that by 100K. And we know that's equal to 0, because I minus is equal to 0. So if I continue working on this, I could say, well, I got a bit of a problem here, don't I? One equation with two unknowns, but what do I know about V1? Well, I know because of linear operation, another thing from linear operation, I know that V minus has to be equal to V plus, or we could say that V1 is equal to V2, right? So what is, and while I know the current 0, I don't necessarily know that these are 0. Back here, there's our summary. The currents, they were 0. The voltage, they're equal to each other. I don't know other than that. But what's V2? Well, the voltage across there, the voltage across that wire, there's no resistor in there. That has to be equal to 0, right? So if you put 0 in there, what's V1 equal to? V1 has got to be equal to 0 then. So I could put that as 0. I could put that as 0. Now I'm getting somewhere. I have 1 over 25K plus V... Did I mess that up? No, I'm good. Plus V0 divided by 100K is equal to 0. So if I solve for V0, I have that V0 is equal to minus, well, I'll have 100K times a minus 1 over 25k. Cancel the k's, and you have that V naught is equal to minus 4. Now the one thing that we probably want to look at is we want to ask, is V naught between our plus and minus VCC, our supply voltage? And what do we know those usually were? If this wasn't told, sometimes they'll put it here and they will tell it to you, but usually it's plus and minus 15, plus and minus 20, maybe plus and minus 10, somewhere in that range. We're probably okay with that. Okay, need units there. So V naught turns out to be minus 4 volts. Minus 4 volts. Okay. And like I said, dealing with these is really pretty easy. We do the same thing over and over again. We do a Kirchhoff's law, and we essentially do node analysis. Well, let's try another one, maybe a little bit different. Sure I got this right. Yeah. Okay. So it's going to look a little like this. But let's say that we're given this, we're told, again, we've got 1 volt. Oops. I don't want a resistor there. And put our feedback over here. And we'll say that, we'll say same thing here, 100 k ohms and 25 k ohms. And then I'll change it up a little bit over here. Instead of just having a dead short to ground, I'll put a voltage source here. We'll say that's 2 volts. And there we go. Back to ground there. Okay. And again, in this one, given this, we would like to find V naught, assuming linear operation. Okay. So what do we do? Well, let me assume a current here. We could assume it either way. I'll just take it going this way. I'm going to say this is IS. I'm going to take this one, IF. We'll say that's I1. No, not I1, I negative. We'll say that this is I positive. We call this point 1. We'll call that point 2. So if I do Kirchhoff's current law at 1, again, like I said, you always do these the same way. We can say IS is going in plus IF is going in. And that is equal to I minus that's leaving. We recognize with linear operation this has to be equal to 0. So now if I talk about IS, I need to talk about that voltage, which is going to be minus V1 plus 1 divided by 25k plus IF. Now I have to find the voltage that goes that way, right? So minus V1 gets me down to here, and then V naught plus V naught gets me back up to there. I divide that by 100k. Set that equal to 0. Again, a nice equation, but two unknowns, V1 and V naught. So we used this. That was our linear assumption. One other thing with our linear assumption is that V1 is equal to V2. Well, what's V2? V2 is now this voltage here, isn't it? So V2 is equal to 2 volts. So we know that V1 is equal to 2 volts. Okay, with that then I can come over and say that I have Let's see, we'll move, what's the best way to do that? I think I can just put in the 2 volts there, so I'll have -2, so I can say that I have -2 plus 1 is -1 over 25K plus a -2 over 100K, is that right? Yep. Is equal to, when I move that V0 over 100, it becomes negative, so negative V0 over 100K multiplied by a negative sign, and then I'll multiply by 100K, so I have 4 plus 2, right? Because I'm going to multiply this whole thing by minus 100K. So we've got 4 plus 2 is equal to V0. So V0 is equal to positive 6 volts. Okay, and again, does that seem reasonable? Yeah, it's between plus and minus 20 or 15. You know, if this was 16, I might start getting nervous. If it was 60, I would say that we had a mistake somewhere, or it was an ill-designed problem, not a very good problem. So I think that's good. One practical thing is probably worth talking about. So when we go down to build this in laboratory, we'll probably put a resistor in here. So we'll come back right in here and we'll put a resistor. And does that really change anything? Well, from a practical standpoint, it gives us a little protection with this source in here. From our analysis, is V2 still 2 volts? Yeah, it's absolutely 2 volts. Because what's the current through there? Well, we know that I minus is equal to 0 and I plus is equal to 0. So V is equal to I times R. You put 0 in there and the voltage drop across that resistor is equal to 0. So while we might put a resistor in there for protection, the voltage drop across it is going to be 0, and that would not change the analysis of this problem at all. Well, that's a couple, hopefully pretty good problems to show you how this works out. There's a couple of really classic circuits that come in this, what's known as an inverting circuit and a non-inverting circuit. We've actually touched on one of those here. But we'll do those in abstract with variables so that we can get some results and apply those fairly easy. We'll do a couple other problems in this area, and that will really wrap up our work for operational amplifiers. So we'll do that when we get together next time. Take care till then, and thank you for watching.